Okay. Hello, everyone. Welcome back, and thank you for joining us again today at the Aspect Final User Forum. Just let's wait few minutes, 1, 2 minutes, to the attendees will come, and then we can proceed. Okay, so my name is Simone Taddeo from Euro-Mediterranean Center of Climate Change, and I will be moderating this second day of the Aspect Final User Forum. Yesterday, we started building what we called a community of interest. Today, we make like a step further and begin shaping a real community of practices, so grounded in experience and concrete application. So before we move forward, let's take like a moment to briefly revisit what we discussed yesterday during the first. But before proceeding, I remind you the housekeeping rules. First, today's webinar is being recorded, so we will be able to share a link with you after the event is complete. And we welcome you to revisit the content yourself and share it also with your colleagues as well. We also invite you your comments and questions, especially please use the Q&A chat box on your screen. So if you think of a question for the speaker at any point, just type in there and I will either pose it to our speakers at the time or I will hold for the discussion portion in the event. Thank you. So just briefly recap what has been said yesterday. Yesterday we presented the Aspect project, highlighting its seamless approach, the co-production process, and the types of climate information developed to support decision making. This was followed also by Frederick Sperman Wayland, who shared insights from the climate project and practical examples of how climate services can strengthen decision making. So the first panel was instead more focused on the user experience and the co-production process, bringing together super users from diverse areas, so from agriculture, from governance, from energy response, and the discussion explored how users' needs were translated into indicators, the usability of climate information, and the challenge of bridging science and practices. The second panel instead was addressed the upscaling potential of climate services across sectors. So it was a moment of reflection with super users about the possibility of upscaling potential climate services across different sectors. And the session concluded with a presentation on the Aspect digital handbook and tools, so followed also by closing remarks. But today, as I said before, we have another full interesting agenda, and it will be sure to present you Bina Balan Sarogini. So today we have her as a first speaker, followed by other three interesting speakers, and then we have other two guests from other sector, and then we conclude with the panel discussion with a round table. So this is the outline of the agenda, and then now I'm going want to present you the first speaker. As I said before, Bina Balan Sorogini, who is a member of the Predictability of Weather and Climate Group at the University of Oxford, and she co-develops aspect methodologies and connect scientists with external users to enhance climate prediction application. So, Bina, when you're ready, the floor is yours, and thank you for your presence here.
Thank you, Simona. Hello, everyone. Thank you very much. Hello, everyone. I'm Bina. I'm going to tell you today about how climate predictions can be used towards creating seamless climate information across timescales. First, I want to tell you about the existing and new climate information which are available across timescales, and how in aspect we have generated new climate prediction ensemble, and how these two can be used to generate further seamless climate information. Some of you might wonder, there are different words: timescales, prediction, ensemble, seamless climate. These are the type of words I will be explaining throughout my talk. Next slide, please. So, what is the difference between climate projections and climate predictions? For example, most of us use the Intergovernmental Panel on Climate Change type of model simulations to assess environmental changes. And then we have also heard of climate predictions or forecast. Example, seasonal forecast. If I use predictions and forecast, both means the same. So the difference basically between climate projections and predictions is that from climate projections, we assess long-term changes, whereas from climate predictions, we can have a nearer-term outlook. Another difference is climate predictions also start from a more realistic start point, so that they represent the natural variations in climate, the ups and downs of the natural climate variations. So seasonal models are mostly available for producing predictions 6 to 7 months ahead, and decadal models, for example, produce decadal predictions from 10 years ahead. And as I mentioned, climate projections are forced by possible future choices of emission, and sometimes called as scenario runs. So on the right, we can see examples of both of these things. Climate projections based on different future emissions, showing global surface temperature change relative to the pre-industrial time. And on the top right, I show an example for El Nino and Southern Oscillation, which indicates a tropical Pacific sea surface temperature with natural variations. And this is, we call it El Nino and Southern Oscillation, the ENSO forecast, started from the 1st of March this year. And we can see that warmer conditions are forecast, which means chances of developing very high chances of developing El Nino in the tropical Pacific, which has wider consequences around the world. Next slide, please. Here I want to quickly show you what climate information are available across time scales. It starts from short-term weather forecast, from subseasonal forecast to seasonal, to decadal, to long-term climate projections. So these climate predictions and projections are ranging from days to centuries. So information ranging from days to centuries ahead. And in aspect, we focus on this time scale or the time period in which the future information is available. And the peach colored box shows the aspect climate predictions. We have also produced two new sets of prediction experiments in the 1 to 3 years time scale and 10 to 30 years time scales. This is novel in aspect, and we will hear more about the results of these experiments in the following talks. Thank you. So why do we use many simulations, we scientists call it ensembles? Climate is chaotic, meaning small differences at the start point of the prediction can make quite a big difference in the forecast information we get. For example, the red line, if it is a single simulation, you could reach the point which is marked X here. Whereas from the climatology or information averaged over many decades, we know that the information can span in this space. In order to span the whole space of information plotted here as dotted dashed lines, we can make, instead of making single simulation, we can make an ensemble of simulations, many number of model simulations to capture this possible ranges of the outcome. And it requires large ensemble production in operational forecasting centers, requires large supercomputing power. And the use of ensembles will also help us get information, probabilities and ranges of information rather than getting a single answer. Next slide, please. So as I mentioned earlier, Aspect has produced innovative prediction experiments in the multi-annual and multi-decadal timescales. These are going to be discussed next. Thank you. So this is our consortium partners across Europe have produced these experiments. The Barcelona Supercomputing Center, the Centro Euro-Mediterranean CMCC in Italy, and Max Planck Institute for Meteorology, and the European Center for Medium Range Weather Forecast, and the UK Metaphys have jointly produced this similar set of experiments. So we heard about the difference between climate predictions and projections. We have seen what type of climate information is available across different time scales. We have seen the importance of using ensemble, many number of simulations to gauge probabilities. And now I want to tell you about the novel methodologies we developed in Aspect to create seamless climate information. Obviously, one way to look at it for the users would be to analyze the new type of experiments created in Aspect spanning different time scales. Another way of approach would be to create seamless climate information using combining or merging information along time. So this will, for example, climate information from different predictions like seasonal to decadal climate predictions combined with observations and climate projections can be used to create a single time series. So the user do not have to go through the confusion of having to choose different products and not knowing which one is the best. Instead, we create a single seamless forecast product which spans across multiple timescales. Here on the right, I show this methodology is called temporal merging, and this particular one has ENSO, the El Nino Southern Oscillation forecast made from made from May 1997, and the purple line here shows the merged forecast, whereas black shows the observations. So this merging method is produced by the Barcelona Supercomputing Center colleagues, and this is a complicated task. And we have, I will also show you another example. Second slide, please. Yeah, so this is an ensemble pooling method generated by the Oxford University partners. So what we have produced is we merge different type of prediction spanning from seasonal predictions, annual 13-month predictions, and 24-month predictions. So the analogy here on the left is like different slip roads or roads joining the main road. So here it's a 24-month forecast, that is the 13-month forecast merging later, and at the last is the 7-month seasonal forecast. So they are all together going to the destination, which is our target season. For example, spring frost. We need a spring frost risk information for wine farmers. And on the right is again a similarity to this traffic road merging I just explained to the ensemble of seasonal, annual, and interannual predictions we created. So this is another method for generating seamless forecasts spanning multiple time scales using pooling ensemble members similar to different cars joining. Thank you. So I hope I have explained 5 elements of understanding climate predictions towards generating seamless climate information. Thank you.
Thank you very much, Bina, for this interesting presentation about seamless climate information. Now I kindly invite all the participants if they want to have like some curiosity that we have like a dedicated Q&A session at the end of the next 3 keynote speakers that I will present right now. I'm talking about Nick Dunston, Dario Nicoli, and Ichi Wang. So let's move first with Nick Dunston, who is like a Met Office science fellow leading the climate dynamics group working to understand the mechanism that drive regional climate variability in different parts of the globe. And prior to this, Nick worked mainly in the area of decadal climate prediction and managed the development of the first high resolution version of the Met Office decadal climate prediction systems. We have Dario Nicoli, who is like a junior scientist at the Euro-Mediterranean Center of Climate Change Foundation in Bologna, in the climate variability and predictability division. His research focuses on decadal climate predictability and coupled modeling for the Euro-Mediterranean region and the North Atlantic, also like contributing to the design, execution, and analysis of CMC6 decadal prediction system. And lastly, we have Ichi Wang, who is like a senior scientist at the Swedish Meteorological and Hydrological Institute, and her research interests include multi-scale interaction in convection, extreme weather, and climate variability, and regional and downscaling. So, thank you all for stay here, and I will now like ask Nick to share like the slides, and then if I remember if the participants has like some question, please fill in the Q&A box. Thank you very much. Please, Nick.
Okay, I hope you can all see the slides okay. So it's a pleasure to talk to you today. Bean has given a really nice introduction there to climate predictions. So I'm going to focus on the interannual timescale. So that's really between the 6 months and 3 years. This is a timescale that's not been very well explored. It lies intermediate between the seasonal predictions and the decadal predictions, which are both operational WMO activities. But many users often want sort of longer lead time information than seasonal. So typically we look at a 1 month lead time with seasonal predictions. But often users want to know what's going to happen next year or what's going to happen next summer or next winter. And so there's a definite need for information about slightly longer timescale, but still with very large ensembles and with the sort of latest models, which aren't often used for decadal prediction given the expense. So what we've done in Aspect is really set out to explore this timescale for the first time in a methodical way to really assess what level of skill is possible in that sort of 6 month to 2 year prediction period, and what can we learn from the different models that contribute to our experiment here, and what can we learn from the model differences. So what are some models doing right? What are some models doing poorly? So we've basically put together the largest multi-model ensemble yet to explore this timescale. So with internal to Aspect, we've had a number of our partners produce simulations, but we've also received some contributions from what I've called here the friends of Aspect. So that's colleagues in the US, Canada, and Japan. And so we've got 11 different prediction systems, which is over 200 members in total, which is a very large set. And we're looking at predictions. So we're doing retrospective forecasts, so hindcasts, starting on the 1st of May and the 1st of November, running out for 24 months into the future for every single year from 1981 to 2023, to really assess what the level of skill is on this timescale. So if we step back and think, what are the key physical processes that can drive skill on the sort of 6 months to 2 year timescale? So this is a nice cartoon here that shows all the different aspects of the predictions. So we are initializing them close to observations as we possibly can at the start of our forecasts. And then we are running them forwards with boundary conditions, for example, changing greenhouse gases, solar variability, etc. But the key processes on this timescale are probably ocean dynamics. So thinking particularly about the El Nino Southern Oscillation, which is really the cornerstone of seasonal prediction. But it's not just limited to a few months ahead. And so it's predictable out to a year or even 18 months in many cases, or 2 years. There's other sources of skill, of course, as well, like upper ocean heat content. So particularly thinking in the extratropics, where often the ocean connects to the atmosphere and can go quite deep, and that can provide long memory as the seasonal cycle of winds deepens that mixed layer of the ocean, and so that can influence our climate. And also other things, like, for example, like sea ice memory, soil moisture, or even wave-driven dynamics in the stratosphere, high up level of the atmosphere. So there's always different components that we think should give us some skill, hopefully, on this timescale. So if we look at some of the results of our experiments, here we're showing the skill of predicting ENSO, the El Nino Southern Oscillation. And what we've got here is on the left, our simulation is starting on the 1st of November. So this is the first point here is the first 3 months. And then we continue on month at a time, increasing the lead time. You can see that our skill drops. So this y-axis is a measure of how well we can forecast ENSO. 1 would be a perfect forecast, which is where we start. You can see that we decline after that, but the skill is still a very useful level of skill by the second winter. So over a year in, we are having a good level of skill. And you can see that the dark thick line here, which is a multi-model mean, so this is the average of all the systems, and that shows the most skill at most of the lead times. But you can see that all the individual systems have skill. They're out at 1 year ahead. You can see there is a spread. So this is encouraging. It shows that multi-models got the highest skill, and we can really try to exploit global telecollections from ENSO. So ENSO affects global monsoons, rainfall, drought, and it even affects European winter. So it's a key mode of variability, and if you can predict it to beyond a year, that's really encouraging. Let's quickly go through 2 other examples. So we have high skill in the North Atlantic, we call the subpolar gyre regions. That's really high up in the North Atlantic, sort of to the west of the UK. So here we can see skill is very high. It actually increases in the autumn as the winds increase and we reconnect to the deeper ocean. So while most of these systems are very good at predicting this sea surface temperatures in the North Atlantic, you'll see that 3 systems are not so good. And I don't have time to show it here, but these 3 systems then do not have such a good prediction of the atmospheric circulation and the winds that then drive surface climate over Europe. So again, here we're showing that most models do a good job, but it's really important to initialize the models correctly here. Similarly for the QBO, the quasi-binary oscillation, that's in the stratosphere, and 2 of our systems show very high skill at that, but most of the systems don't. And that's again because some of these models have not been tuned to reproduce this, or they don't have very many layers in the stratosphere. So this is again another area where we see potential for improvement. Finally, I just wanted to show 2 quick challenges, really, highlight 2 challenges in the application of interannual climate predictions going forwards. One is that the skill, where the predictability really is often in the large scale circulation. So it's not taking grid points over a particular small area that's local to where you want to look at. Sometimes the best way to get the information is to look at the large scale circulation patterns like the North Atlantic Oscillation shown in this cartoon here, and then to really take the predictable signal there and to downscale that to the local information. And so that's something we'll be working on continuously going forwards from Aspect, because sometimes these circulation signals are quite weak in our current models and they don't produce the downstream sort of impacts in the strength that we would like. So there's still lots of research going on in this area, how to extract these signals and make the most useful prediction information. And that's particularly true over Europe. The other, I think, challenge is to really try and exploit windows of opportunity. So prediction skill is often intermittent. It varies from year to year. And when you assess it over all years, the average sort of level of skill can be quite low. However, there are often windows of opportunity when there's a very strong driver happening. For example, a very strong El Nino event. And actually, that's what I'm showing on the top here, which Bina showed in her presentation as well. At the moment, we have a forecast for quite a strong El Nino developing in the second half of this year. And so this is an example of a window of opportunity where we might have more skill and more robust confidence in our long-term predictions. So trying to know how best to identify and exploit these opportunities is key. So that's just basically the summary. This is a timescale that we are investigating. It's still very much a discovery science activity, but I think we are showing that there is considerable promise for early warning at lead times above 6 months for a number of different variables and regions. This will help to bridge the gap between seasonal and decadal information. I also note we find that skill does not always monotonically decrease with lead time as we go out further ahead. often skill re-emerges because it moves through the climate system and in different components. The multi-model mean is still often the most skillful, and that really really highlights the benefit of combining prediction systems to give the best prediction. And we have highlighted some key shortcomings in individual systems. And finally, I just wanted to note this interannual prediction timescale will be examined for the first time in the upcoming CMIP7 decadal prediction project. So that's also exciting. I think Aspects really led the way in trying to sort of explore this timescale. So hopefully we'll see more promising results in the future on this. Thank you.
Thank you very much, Nick. And now we will keep like all the question at the end. Now it's like the turn of Dario. Dario, over to you. We can see your screen. Okay, perfect. Thank you very much.
Okay, can you hear me?
Yes.
Thank you. I'm Dario Nicoli. So today I'm going to present this work about the extended prediction to the next 20 years, carry on within the WP1 and WP2 umbrella. So the idea to extend initialized prediction up to 20 years is something that was already started several years ago, but just during the recent years, it has been started to be explored, in particular with these two work provided by Dusterus and Brun in 2024, Mahmoud et al. In 2025. But why are so important? First, because climate adaptation and policy require prediction which extends beyond the year 10, but at now the only available product is the uninitialized projection, which substantially means predictable internal variability, which is crucial to catch the climate at multi-decadal timescales. So this represents a strategic opportunity to assess predictability of the extended decadal prediction, and this work represents the first explorative and comprehensive multi-system assessment of this kind of predictions. In particular, we aim also to answer to some key research questions. So if the initialization provides added value beyond the first decade, and how this predictive skill evolves across this time horizon. What are the impact of the model drift and biases on long-term predictive skill, and if we are able to identify physical mechanisms which sustain this skill into the second decade. Moreover, we also want to assess the limitation of this exercise, and hopefully this limitation will be overcome in the future. So let's see the experimental design. On the right, we have a table in which there are the models that join to this exercise. We have 6 different fully coupled climate models. We aim to cover the period 1960 to 2025, initializing the simulation every 5 years. This means that we have 20 years long simulation for each start date. We have collected more than 70 members from initialized 20-year prediction, hereafter init, and uninitialized simulation, so the ensemble of historical and projection, hereafter no init. But it's important to keep in mind that this first exercise has some known limitation. For instance, the limited sample size, the fact that we initialize the system every 5 years constrain for sure the statistical robustness of the results, and also the relatively short hindcast period compared to the predicted timescale, 20 years versus 60 years. Moreover, we have the usual limitation of prediction, which are the representation of key physical mechanism by the model, as well as the spatial resolution of themselves. We can for instance, considering that all this model has a horizontal resolution which spans from 2.8 to 0.7, so does not resolve part of the ocean dynamics. But knowing this limitation, we can try to assess it. Let's have a look to some results. First, here we have the annual surface temperature, we have the ACC of the multi-system, so we consider the model as a whole. The first, the left column represents the initialized 20-year prediction. The second column is the difference among what? Among the initialized prediction and non-initialized prediction. So we can say that this is, let's call it the gain in skill that we gain we have in each forecast year. So the ability of the model to predict, for instance, 1 to 5 years to predict the climate 1 to 5 years in advance. So focusing on the last two rows, forecast year 11 to 15 and forecast year 16 to 20, we can see that compared to the non-initialized simulation, we have a low degree of skill. In particular, for forecast year 16 to 20, we can see that over the subpolar North Atlantic, we have some degree of skill. But to better understand, we can analyze the residual correlation, in which substantially this method assumes that the ensemble mean of an initialized simulation can be considered as a, let's say, a representation of the externally forced signal, even if this is a really strong assumption, but it is useful to better assess the impact of the initialization. Focusing on the last two rows, again, forecast year 11 to 15 and 16 to 20, we can see that there is some significant results covered in the North Atlantic Ocean, in particular the subpolar North Atlantic and the subtropical branch. And this is very important because that area is particularly important for the one index, which is the Atlantic multidecadal variability, an index that has several teleconnection over the global scale at these time scales. And we can see that the prediction outperform the historical and projection in predicting this index. Another important index is the North Atlantic Oscillation Index, as already presented by Nick for the other timescale. And also here we can see that there is some degree of predictability for the initialized 20-year prediction compared to the non-initialized. Another important aspect that we are analyzing is the evolution of the biases in forecast time. In other words, the drift. We can see the forecast year 1 to 5 on the top row, forecast year 16 to 20 in the bottom row. We can see that each model features the biases differently through times, but there are there is a common feature. In particular, the subpolar North Atlantic SST, we can see that for each model there is this growing cold bias with grow and grow in forecast time. And for the first time, we can see that this drift does not converge toward the model attractor, but instead has own model attractor, different from the uninitialized simulation. Another let's say important aspect that we have to analyze and with respect to this sea surface temperature is the Atlantic meridional Hamiltonian circulation, which is substantially a proxy of the northward transport of warm water toward the high latitude. In fact, we can see that the drift in this case, in case of the HEMOC, is particularly is not particularly strong for all the models, but each model features differently. So we are now analyzing this drift and trying to look at the mechanism that sustain this drift over this area. So just to summarize, this is the first explorative comprehensive multi-system assessment of the extended decadal prediction. It's important to repeat that there are known limitations such as the limited sample size or the short hindcast period, but we got some promising results. In particular, we have seen that the initialization effect persists, so there is positive ACC for surface temperature also beyond the forecast year 10, and we have seen that there is some indices such as the North Atlantic Oscillation and the Atlantic Multidecadal Variability, particularly important for the downstream climate of the Europe. And we can see that this indices has retained some significant scale also for beyond forecast year 10. Nevertheless, we have to consider that the model drift, we have this model drift from early forecast year, and each model converges toward its own dynamical factor and causing this growing cold bias in the North Atlantic subpolar region. Thank you.
Thank you very much, Dario, for this interesting presentation. Now I would like give the floor to Ichi Wang, and then we have a few minutes for Q&A. Ichi, please, when you are ready.
Yes, let me share my screen here. Do you see now?
Yeah, perfect.
Hello, everyone. My name is Ichi Wen from SMHI. It's my honor to share our collaborative work with SMHI and the University of Zagreb on the extreme events studies over the Emilia-Romagna regions. And we will especially focus on the extreme rainfall and the heat wave based on our discussion with stakeholders there. So our goal is to really provide the high resolution information on extreme events to support the region's adaptation planning and risk management. And our approach, called event-based downscaling, has 3 features. First one is that we really focus on the extreme events. And the pipeline is actually very flexible, could be customized to any extreme event of interest. And the second one is that we would simulate these events at a local scale to the kilometer square scale to facilitate the stakeholders' use. And the third one is that we use this approach to assess how these events' intensity and impact may changes in the futures. So why do we need a new approach for extremes? There's 3 reasons here. First, when we do the long-term climate simulations, it's very hard to really get information of extreme events because extreme events usually show at the very tail of the distributions. So in order to get enough statistics, very long simulations is needed. The second reason is that usually those global climate models that we use to predict the future climates usually has a very close resolution. As Dario just showed in the climate prediction models. And those model resolution probably too close to directly use for the users in the regions. And third one is that the decision makers really need the local information in order to do the planning. As the Emilia-Romagna region here, it includes the plain and the mountains, which are very important for the different planning in their regions. So our approach actually include 2 stages. The first stage is the detection of extreme events. So from the global climate simulations, we could select the extreme events from our discussion with the stakeholders. And for the current historical climate and for the future event climate. So here is an example of using the threshold, like choosing these 3 days of the event definition. And then after getting the event, we could use our original model to downscale the events from global scale to 12 kilometers and to local scale 3 kilometers to get the refined features of these events. So this is especially emphasized with the co-development with the local stakeholders. In this project, we collaborate with APARI in Emilia-Romagna. We really have a very good discussion about what's the most relevant events for their climate risk and decision needs. So eventually we come to 2 events. The first one is this heat wave events, especially over the cities like Bologna. They are very concerned about the daytime heat wave, which is getting serious in recent summers, and also this nighttime urban heat island event, which will disrupt people's sleep and health very much. And they're also very concerned about these extreme rainfall events, which is often related to the Mediterranean cycle, which like a storm Minerva that really brings a basin-wide rainfall and causing the flooding in 2023. So this is an example of the rainfall extreme that we focus on. So as I just mentioned, that this is a storm Minerva occurring on May 16th, 2023. You can see the storm is just over the Italy and bringing a lot of rainfall over Emilia-Romagna region, which can up to like 20 millimeter per day. So in practice, we will detect those extreme rainfall events from the climate simulations in around year 2000 and downscale it to 3 kilometer resolution. And we will do tens to hundreds of them in order to get a distribution of the characteristic of the events. The same approach or then apply to the climate scenario of year 2040s. And again, we will downscale those events and get the statistics of these events in the future scenarios. So for the heat waves, here we will focus on the daytime heat wave, which will related to maximum temperature about 35 degrees, and the tropical night equatorial night events, which related to 20 degrees or 25 degrees in the daily minimum temperatures. So this is an example of the nighttime urban heat island. So here on the left-hand side is from the observations. On the right-hand side is the same events that simulated with our approach. You can see that over the Emilia line, these line of cities are very significant, showing the higher temperatures than ambient regions, which will very important health impacts. So again, we will apply the approach with these heat wave events and eventually get the two distribution, both for year 2000 and year 2024. So eventually, in this project, our group will provide an extreme event catalog for Emilia-Romagna. So this catalog will focus on the main extreme event that I just mentioned, and for the historical period over 2000 and the mid-century period over 2014. So this data set will include the intensity, duration, and the maps of impacts that related to the heat wave at each rainfall, and could leave the stakeholder to explore and further use in their decision making. So what we learned from this approach, we are very glad that we have collaborated with Apari, which provides us very decision relevant context, so we could customize our approach to provide those information that hope to really help their decision makings. And these results and data set will integrate into aspects of climate services prototype, and hopefully in the future could be applied to other regions and other events. Okay, that's all for my talk. Thank you for your attention.
Thank you very much, Ichi, for the presentation. And now we have kind of like minutes for Q&A session, so with our keynote speakers. So please feel free to submit your question in the Q&A chat box at any time. Also, we have like some question like already. The first is related with Nick. So Nick, we have like a question for you. Other than the assemble sides, what are the major differences between what is possible and the prediction skill using the multi-annual prediction presented compared to what we currently have available from the decadal prediction system and the global annual to decadal update?
Okay, yeah, I can definitely answer that one. So it's a good question. I mean, fundamentally, they are very similar, but what we're looking at here is a 1st of May start date as well. So the decadal ones just have the 1st of November, which means we can look at winter at 6 months, or we can look at winter at 6 months and summer at 12 months ahead. So that's sort of basically a second start date to help fill in that different lead time information. I guess we also wanted to have larger ensembles of more modern models in that. So, for example, the ECWF CS5 system, it doesn't run in the decadal mode, was able to run, which is one of the best seasonal forecast systems, was able to run in this experiment out to 2 years. So we're exploring models with slightly higher resolution components and larger ensemble sizes than we normally explore in decadal. So I guess those are probably the two main differences.
Thank you very much, Nick. And then we have like another question, I think like related to Bina. Is it possible to share with users the skills of each of the different sources that have been combined? And how will you convey the weight given to the skill of different forecast prediction model at different lead times? And this is like a question from Emma from Save the Children International.
Thank you, Simona, for reading that question out. Thanks, Emma, for asking this very relevant question. With respect to the first part of your question, in the example I showed in my last slide, where we used different prediction types to merge to get a combined, robust, seamless forecast for spring frost risk information for Catalonian wine farmers. In that particular methodology, we have used equal weightage to all ensemble members and all prediction types. And with regard to your particular application for the Malawi rainfall forecast for emergency humanitarian sector user need, this is the method as you have been talking to our BSc colleagues like Carlos Delgado. So this particular method uses a process called a methodology called sub-selecting. So in this method, those simulations which follows a seasonal prediction or observations in the short term is chosen to is chosen in the decadal predictions and the long-term projection. So the added value of using which method for your own particular use, either to go for the seamless forecast or to go for a particular type of prediction experiment, is depending on the added value. And I think this is an ongoing conversation we have with you through the Barcelona Supercomputing Center colleagues. And we will be happy to continue the dialogue to provide the particular skills what you are looking for. Thank you.
Thank you very much, Bina, for your response. So at the time, we have no additional questions, but I encourage to all the participants to submit additional questions in the Q&A chat box at any time. And I would like to thank you all the keynotes panelists invited. Thank you very much for your brilliant representation. Thank you very much. And now we move forward with our new guests. So now is the turn of Haralampos Karvelis, who is data engineering and methodologist at the European Center for Medium Range Weather Forecast, working in the data archives and dissemination teams as a data management and services engineer. So he specializes in data governance, processing, and management, ensuring efficient and reliable data services. So thank you very much, Haralampos, for your presence. And when you are ready, we can share the presentation and everything.
Yeah, we are going to introduce a bit about the data documentation, and then we will continue about how to access the data, how you can download, and we briefly present some kind of the graphical products results that we have, and finally we are going to conclude with a summary and some keynotes that you should take from this presentation. So Aspect is a very complex project with a lot of different data. We are dealing with multiple data sets, different data types, very large data volumes. And in the project, we are also span across different time scales, as you already see, from seasonal forecast to the decadal, severe to longer term outlook. So another very important aspect of the Aspect data management is we want to find a way to transition from the research workflows to more operational services. And this creates additional requirements in terms of robustness and sometimes also we need to reproduce the data. So because Aspect is so complex project, from the very beginning, we had our data management plan, which plays a very central role as it defines how the data are formatted, how the metadata are structured, and also how the data archived. And this was more an internal document for our partners to collaborate all together. The strategy that we follow in order to support this Aspect framework was to develop two main documents. The first was the catalog with a clear access point of the data, and this document acts as an entry point for the users to help them to understand where the data are located. And the second is the Aspect documentation, which provides detailed information about the data sets and also about the models that we are using. In addition, we are working on the Aspect data portal, Aspect Data Hub, which is aimed to provide more centralized and user-friendly interface to access Aspect data. So for Aspect documentation, first of all, our approach is that the Aspect data should be self-describing as possible. So in order to achieve this, we use some well-defined metadata in the community and also standard conversion. However, metadata alone is not enough, so the documentation becomes the main interface between the data and the users. And it helps users discover what exists, understand what the data represent, and use them correctly. So an important principle of that documentation is that we didn't add this at the end. It was developed continuously, and somehow we try to embed it in the delivery system that we have. And this means that when the data are produced and delivered, the corresponding documentation is also created and updated. And the documentation provides the structure of the data sets, the model, the experimental designs, information about the variables, the frequencies. And yeah, I will show in the next slides what you can find in the documentation. And also, before start show you a bit more about the documentation is organized by the time scales and the forecast horizon. So this includes the seasonal forecast, the multi-annual predictions, the decadal, the longer term outlooks. And this structure is important because different users are interested in different time scales, and in organized in that way, user can quickly navigate to the section that it's most relevant for their application or needs. So if we go to the documentation, one key component of this documentation is the description of the experimental design, and this explains how the simulations were produced. For example, it include information about the forecast period, about the sample size of its system, the initialization method, and all of this information is very essential because the users need to understand the context of the data before start using this data. So without this information, it will be a bit difficult to interpret the result correctly. But also we not describe the experimental design, but also we describe the system, the forecast system itself, which is another very important part of the documentation. And this includes both the scientific and some technical description of this of the models. And you can see in the slides what this scientific documentation contains. So this helps users to understand the differences between the systems and to have a better insight of the data that they are using. And it's very important because when you're comparing data sets or comparing results from different sources, you need to understand better what the data contains. So here you can see an example of the details that we include. So this type of information is essential for sometimes maybe to more advanced users. So for instance, a user may need to understand what is the petrobustion strategies that we follow, the resolution differences, how the initial conditions generated, and etc. And all this of level of transparency is a key for reproducibility and the scientific analysis. In terms of data access and moving more to the documentation, we have to encounter another level of complexity. So aspect data are not stored in a single infrastructure, not in a single archiving system. So instead, they are distributed across different archiving infrastructure. So this means that the access method, the format, the workflows can vary depending on the data sets. So for the user, this can also be challenging, and this is why we need guidance, and we create all this documentation and provide all this information. So, for example, for seasonal data, the main entry point is this document that I start with, which is the catalog of the clear access points of the data, which provide and give you all the links that are relevant for aspect data. So someone using this document can redirect to the correct place. So, for example, continuing with the seasonal forecast, all the seasonal forecast is stored in climate data store in CDS, which is the key access system for seasonal forecast. So CDS provide both the data, but also its own documentation. And together with the aspect guidance, it helps users understand how the data sets are organized. And to continue with the next slide, this show a practical example of the CDS usage, and the key point here is again the metadata, and the user need to select the correct sender, the correct system version, of course, the correct variables and time range. So without the proper understanding, it's very easy to select wrong data sets. Continue with the decadal and other data set. Again, in the catalog that we have created with the main entry points, someone can detect where our decadal data archived. And in this case is in ESGF or in DKRZ, depending on the data sets. So again, if you redirect to where the data real exists, you can see at the beginning when you start using ESGF, there is also documentation from ESGF itself, and combined with the instructions that we try to provide from Aspect, you can have the full knowledge of how you can download the data. So this can make easier understanding the data. Continue with this. The metadata, again, is another example here that plays a crucial role. So you can see in our documentation, we have described very detailed what you need to put in the ESGF search in order to find the correct metadata, the correct aspect data sets. And this is, again, a very detailed example of how someone can filter ESGF in order to get the proper data. So you can see here is an example from the BSC model, and adding all this information here, filtering ESGF, you can have the proper metadata, the proper data set that you want. But of course, users not only want to search for the data, but they want also to download. And this is the next step, I will say. So we provide also some kind of guidance through the documentation, and we have some example. And even for more advanced users, there are tools, and we have also some notebooks that support the automated workflows. So for larger data sets, of course, I mean, you can understand that the manual download is not very practical, so you need some more advanced techniques to download and use this data. Also, we not only finish with providing all this information, but also we provide some workflows and some applications, which is some kind on top of the documentation, which can help the users to see the data, I will say, before start downloading this data. So we have a catalog with graphical results, and you can see here all the maps that is produced. So this allow the user, let's say, to explore the output visually. And this can be the first step before start downloading the data. So here is another example of the temporal merging. This is the seasonal to decadal. Again, all this information are available through some signing up developed by BSC. As a summary, I would say that, again, Aspect is very complex and multi-partner project. We have generated a very large volume of data across different infrastructure. And to make this data usable, we rely on the combination of the data management, of the documentation, and a kind of guidance. And now saying about this guidance, we also plan some training activities to support the users and also support the partners. And probably you will hear more about these training activities in the chat. Maybe Adria can share more information about the training. And that's a take-home message. I would say that documentation and metadata are very essential, and they are not something like an optional extra. So you can use the catalog to identify the correct access point, but also a better knowledge of the metadata help our search for the data. And yeah, this catalog is the entry point, and together with the metadata support one each other. And of course, as I said before, the training that will come will help the users to navigate the Aspect data ecosystem. So yeah, thank you very much for your attention, and I'm happy to take any question. Thank you very much.
Thank you very much, Rampos, for this interesting and useful presentation. And it is really good to see how these data are accessible. And I'm sure that many of our useful. For your interest, we have dropped in the chat like an expression of interest to receive information about the user training event. So please like register at the link that is like dropped in the chat. Now, before collecting questions, I want to first like introduce you Chiara Cagnazzo, who is like the principal scientific officer at the European Center for Medium Range Weather Forecast within the Copernicus Climate Change Services, where like she mainly address like the challenge of transforming user needs in different sectors such as energy, agriculture, water, health sectors into usable weather and climate derived information. So her prior research was dedicated mostly to understanding the role of atmospheric variability and its representation in models on climate predictability at time scales from seasonal to decadal, and as well as on long-term climate projection. So please, Chiara, when you're ready, we can start with your presentation, and then we collect some questions from the audience addressed to you and Haralampos. Thank you.
Thank you very much for that long, nice, and exhaustive presentation introduction, Simone. I think I would like to share my screen, and maybe you need to stop sharing yours.
Okay.
Yes, now it's working. Okay. Can you see my screen?
Yeah, we can see your screen at full presentation.
Thank you very much. Okay, so now I think it's my role to give you a bit about some perspective from the European Center for Medium Range Weather Forecast and the Copernicus Climate Change Service. We do it now because, I mean, we are kind of at the latest stage of the Aspect project. There are a lot of lessons learned, and actually the idea is to understand if we can build on top of the Aspect's results from the point of view of an operational organization that implements these elements of operational climate services. So the few reflection slides, I think, would like to cover some elements, not really in this order, but what I will mention is connected to a few examples that illustrate challenges in the process, or, for example, which new integrations can be immediately offered operationally, building really on top of this new user knowledge, and somehow also drawing some conclusions about the legacy. But I mean, the discussion will happen later on. Well, my first introductory slide is a bit on what have we learned, and the starting point is really a reminding which are the challenges that are associated into moving from this research dimension into a more operational setting. So when we think more from a research point of view, of course, these kind of activities tend to be very much hypothesis driven and exploratory by definition. Whereas, of course, when we need to think of implementing operationally a service, we need to deliver something that is service driven and user facing. When we develop the different configurations and modeling configurations that have been discussed so far, of course, in a research mode, they tend to be quite flexible, allowing the exploratory role of the project itself. But then when we want to operationalize, we need to ensure that then we fix them, we decide what we want to go ahead with, and we need to really control these configurations. When we analyze and play with the data in different contexts and within the research environment, often we deal and work with offline simulations. Maybe they are irregularly produced for the scope of exploration from a science point of view. But then when we decide to implement them operationally in real-time production, the service should be continuous in time. And other elements connect, for example, to the fact that we can tolerate failures when we do research activities, whereas when we implement this operationally, this needs on 100, more or less 100% of reliability. And maybe another element is that we have also heard so far quite a lot about skills and skill metrics, because this is absolutely crucial when we evaluate the scientific quality of, for example, a forecast simulation. But of course, when then we implement a service, we need also to take into consideration strongly the robustness and the usability. So just to summarize these very general kind of elements, we need to pass from this optimized for insight design of the project itself toward a more optimized for trust and continuity when we put it operationally. Sometimes what we have learned is that what is the best model is different than delivering a best service. And I think that, and we all think that Aspect helped us in shaping, or actually in understanding, several elements. On the one side is last mile problems and the gaps coming with, and also shaping the next generation of forecasting systems. You have heard a bit from the previous speakers also. So, well, I think the example that I would like to bring here, that probably is one of the most successful examples that we have had so far within Aspect, that is connected to the questions that we are trying to answer. We know that the questions from the users are seamless, but the data and the modeling systems used to address the questions are not. And the research questions that Aspect tried to answer, one of those was if we can bridge in a meaningful way this seasonal to digital timescale. And when we say meaningful, we mean meaningful both from a scientific point of view, from a technical point of view. We have heard from Harris and Harambos a lot of technicalities behind the data, but also from a user-centered way. And we have several case studies within Aspect helping us to answer this question. So the activities of the modeling centers within Aspect help to really design somehow this and explore these 2-year forecasts for answering these questions, and help, for example, to design a protocol to do that. And when we say protocol, we think of technicalities like a forecast length, number of ensemble members, initialization strategies, also somehow shaped by the user needs and demands. It helped, for example, to start generating these new multi-annual simulations. You have learned a lot from Nick how they are working, and somehow those were initially designed on existing systems. There have been several research activities and analysis to learn about new science from these extended timescales, and also the data governance was in place from the beginning, as Harris has mentioned. Well, this slide is actually has been already presented by Nick, and actually is just a quick snapshot connecting exactly what we are talking about when we think of a multimodal setting. And in this case, the aspect in multimodal experiment systems to explore this interannual 2 years integration is, of course, made by this number of models that have been already presented. That is also as a specific strategy in terms of initialization and for realizing these 24-month forecasts. What is very important that it works in this multimodal setting, and Nick has very nicely presented the added value of working in a multimodal system, as in this case for the El Niño Southern Oscillation and the Niño example. So the key bottom line is that we have scientific evidence that there are added skills, and this is why somehow also as an operational service at ECNWF, we plan to serve these timescales operationally now in the next phase. But then, well, then we know that the modeling system also evolve over time. So we learn a lot of lessons in the current system, and they evolve over time. There are new next generation systems that Aspect has helped to somehow design. Several are under implementation, will be implemented and deliverable and delivered. But does this mean that what we have learned from the previous system is not valid anymore? Or can we confirm, for example, that the skills that were found in the previous are also, valid in these next generation systems? And so this is just an example illustrating a bit around these questions. And this is an example that come from ECNWF. And somehow, sorry for maybe the figure is a bit technical, but it shows a metric. This is the anomaly correlation for this extended seasonal forecast at the second year of the forecast with respect to its initialization in November. And in practice, it says that, yes, there are skills at the second year, and yes, these skills are, for the new modeling system, are in line with the old system too. And somehow, maybe in some areas and in some conditions, also a bit better. So Aspect has helped to design this protocol and evaluate the simulations. And in 2026, now we plan at ECNWF to produce them operationally. So to serve the 24 months integration operationally, and also to improve a bit the offer on the first year, the 13 months integrations with longer and larger retrospective forecasts delivered by the end of this year. But you've also learned from the presentation of Nick that there is a great added value also in the multi-model system. And this is where C3S is coming in this conversation. So C3S offers this operational seasonal forecast products. Harris has mentioned a bit how to reach these products and this data. In today's offer, C3S offer this multi-model. You see in the slide that the different modeling centers participate into this effort, and data are delivered operationally, reliably from the climate data stores. Users can download the data, can use APIs, and can play with different statistics, having access to the retrospective forecast, the real-time forecasts, really in a reliable manner. And together with the data, there are also graphical products, because there are many different kinds of applications where it is absolutely crucial to have access to this kind of graphical products more than to the data, or maybe having access to the graphical products before the data. And there is a variety of those products that are already implemented. And because of the many lessons learned, we have heard also from Bina how important it is to merge these multiple timescales. So what is coming next is that we are, EC3S is upgrading the system itself. For example, the ECNWF model will be available with more frequent initialization, longer range forecasts. The models continue to upgrade. But also in this stage, we would like to understand better the timescales of predictabilities for applications at the regional level beyond this current 6-month timeframe. And this is why more modeling system will provide longer forecast. And this will be already available by the end of this year. And in terms of graphical products, again, we have heard from Nick, and this plot has been already shown as the relevance of having these windows of opportunities. And so these graphical products also will evolve, are evolving with better representation of specific elements. And this is an example, for example, of this forecast for the Niño as it was released in March 2026 and the forecasted conditions for the next months. Well, I think I need to go very fast because my time has passed, but I have another couple of elements, maybe 3 elements to illustrate. I will go very fast. The first one is that we have heard also about the decadal prediction system. This is an immediately connected implementation operationally. And actually now the plan is to deliver this decadal climate prediction system service by using 5 different prediction systems and offering together with different data products that will evolve over time, also taking into consideration what will come from CMIP7 specific case studies. And this is again going to be live this summer for a first release of the forecast initialized in November. Well, there are a lot of lessons learned about data governance, but I think we have heard this from Harris, so I'm not going into the details because my last point before closing is about mentioning which are the lessons learned from building climate web applications. Within the Aspect, we have been able also to work a lot in interfaces with the users. So how to lower the barrier and access the data in a way that is actually more meaningful and also more user-friendly. There have been several applications that have been developed in terms of prototype modes. So applications that allow to play directly with the data, applications that are more dedicated maybe for specialized users who want to explore a bit more technical elements. There have also been the possibility to develop, for example, case studies. Those are different kind of applications where you have a narrative. So in one case, you have an application where you really play with the data. In other cases, you can have that your data play or are an integral part of a story somehow, of a narrative. And yeah, we have a lot of lessons learned also in this respect. Again, I cannot go into the details of this, But maybe the key elements that we will build on is the relevance of the co-designed approach, going from a prototype, testing, and refining the cycle through development. There have been a lot of technical learning that we have explored during Aspect and we will use in the C3S new upcoming applications, also in terms of specific tools and libraries that have been developed or used. And my last slide just highlighting this element, which are the synergies and the next steps for these interfaces. Certainly, we will build on top of the lessons learned from prototyping to having something that is stable and operational, also from the interface point of view. We will reuse a lot of these technical developments that we have explored and within Aspect. And the idea is also that we can work also in reaching new sectors and upscaling. And I thank you very much for your attention.
Thank you very much, Chiara and Aralampos. Now, I just collect one quick question about the link of the aspect data. I saw that Aralampos already a response that we have a dedicated web page on the website, but it's still not online yet. However, we have drop also the link for the aspect deliverables for your knowledge. Okay, we don't have any additional questions, so I would like to thank you both the keynote, and now I want just to give a brief a snapshot of the Mentimeter. So it's a way that you can stay interaction with us. So we will love to invite you to participate via Mentimeter, so you can share your thoughts and interact with us more deeply. So this is the link in the chat, or alternatively, you can scan the QR code that my colleague is showing here. And please take a moment to join, and we'll really look forward to your reflection on this. And I want just to let you know that the Mentimeter will stay open for the next few days, so you can access to it and complete it later too. Based on that, I want to also renew my desire for the participants to share your thoughts and reflection through the box of Q&A also later on. And now we are already having some response from our first question. So what do you think about the second day of the Aspect Final User Forum? And we now are receiving many answers, and we are really great for your engagement, for your interaction one. Okay. I think now we wait a few other seconds for new questions. We would also like to hear from your comment and feedback, or if there anything else that you would like to hear about. Please also here share your comments. But as I said before, the QR code and the link will be also available for the next days for additional question or reflection by your side. Okay, so now we move to our final panel. We have several guests where we will reflect on the legacy of the Aspect project and its broader impact. So the discussion will explore future perspective and how current developments will continue to evolve over the time. So I will like to welcome first Chiara again, Cagnazzo, where she will take part of this like round table, but also Albert Soret. Albert Soret is the deputy director of the Earth Science Department of the BSc, as also like an adjunct lecturer at the Polytechnic University. And he's like the principal investigator of Aspect project, and previously he has like coordinated the sub-seasonal to seasonal climate forecasting for energy project. We have also like another guest is Jason Lowe. Jason is like a principal fellow and head of climate services for government and chair in the interdisciplinary climate research in the Priestley Center at the University of Leeds. And his expertise include a variety of knowledge from selection design of climate scenarios, climate impacts, tipping points and high impact events, climate modeling, models and risk assessment, and the application of climate data into real-world sector, including infrastructure. So, thank you very much for your presence here, and now we will look ahead like to emerging direction and new opportunities in the field. So now I would like to address some question and to know like about your personal views from, for example, like the legacy of the project. So from your perspective, what is like the most important legacy of the project? So how can the project make a difference in the future of real world users? I will leave like the floor to Albert and Jason, and then we have like also like additional question just to Chiara as well.
Thank you, Simone. So to talk about the legacy of the project, let's start from the beginning. Okay, so when the project was defined, at that time, different communities in the climate academia sector were working at different time scales. So the people that was working with the seasonal, the decadal, the sub-seasonal, the projections were working in silos and also in working with different systems. And at the same time, also we have the users that they have specific questions that take into account different lead times. So we saw this as an opportunity to do a reflection and to work together. And based on this reflection, in the end, something that has been done in the project has been to develop different methods to combine these systems to work together and to provide consistent information. And also some of these methods are taking advantage of the previous simulations to improve the simulations of the next simulation. So for instance, we are using some methods to select specific members from the decadal using the simulations of the seasonal. Okay, so taking into account this perspective, Aspect was defined as a research project, but also thinking on a specific user needs. Okay, so tailoring the research that we were doing to make sure that at least for some specific applications, there was an impact and an application. And taking into account all this, in the end, it was like the backbone of the legacy of the project. So first, I think that the first legacy of the project is to create a community of practice and a community of researchers working together. So community of practice users at different levels. So people that is using the predictions, people that is also interested in national meteorological services, and also at the same time putting together also the researchers that are developing the models and also the researchers that are doing climate services, all this together. And for instance, one illustration of this community is that in most of the papers, we have been discussing also on the terminology that we are using, because we were exploring new concepts and we were defining new approaches. Okay, so this is the first one. So this creation of a community. The second one is related to the discussions that we had with Chiara and Harry. So on having some simulations and to put them available to the community to explore and to work with this data. The third one is on the definition of new methods, on having access, on providing access to everyone, also to new codes and new systems and new workflows to develop these systems. And finally, we have been working with 5 specific users, highlighting different needs from different regions, from different variables, different timescales. So being able to show specific needs and how the development of the project have been useful for these applications.
Thank you very much, Albert. Now I would give the floor to Jason.
Thank you. I mean, when I think of where we've got to over the years since Aspect started, I break it down into a few different categories also. I mean, I think we have left and will leave a scientific legacy. And we've seen some examples of that yesterday and today. So I think we have improved the initialization systems and the models used in initialized forecasts. I think we do have some new learning around aspects such as boosting the signal to noise challenge that has been holding back the use of these initialized forecasts. I think we've learned some new things about downscaling, and in particular, what particular type of downscaling works in a given situation. And I think we've also learned some really interesting things using post-processing approaches. And that includes the offline joining of information across timescales, and also further developments of the windows of opportunity that you will have seen Nick present. I think we've learned about the process of doing this type of science. And Albert mentioned the super users and the community of interest, community of practice. I think that layering of users who have different amounts of time to commit and different levels of interest in understanding and using climate information has been a real step forward. I also think it's been informative for the researchers, especially in the physical science modeling work packages, to learn about how that user information can actually steer the direction of the underpinning physical science. And then finally, I think it's worth saying scaling is really important. We've learned some things about scaling, and one of those things we've learned is how difficult scaling actually really is.
Thank you very much, Jason and Albert, for your answer. And now I have another specific question about barriers and challenges. So we have seen today how seamless climate information is scientifically promising, but its operational uptake is still limited, as Jason mentioned before. So what are the main barriers preventing their use or limiting their usefulness in climate services today? So how can this change, for example, in the future? I don't know, Chiara, if you want to intervene.
Yes, thank you. Yes, actually, there still are several barriers for the uptake of the climate information, especially the seamless climate information. That's what Aspect want to bring. One is maybe more technical, that is related to data governance. We know that this still remains, to a certain extent, fragmented. I mean, fragmented across timescales, across models, across institutions. Governance can be still inconsistent. We know that the questions are seamless, the data behind not. And we know from where we were starting, as Albert was saying, working in silos, not only as a scientific teams, but also really in terms of practicalities and data management and governance. So I think Aspect helped by starting to define a kind of data management plan, of course, from the beginning. That's very important. And of course, within the research design, it is not possible to enforce practices across, but I mean, we can learn on top of that and actually fill the gaps that are related to this lack of harmonized conventions, metadata, heterogeneous formats, and disconnect also to maybe less clear responsibilities, difficult to interoperate the data. So it's more technical kind of answer to the questions, and some mitigation has already been somehow put in place within Aspect, but we can learn on top of this from the legacy and the next steps. The second important element and important barrier is related to the data quality that is often not sufficiently user-oriented. We have learned this a bit. The quality maybe is often defined more scientifically, not fully in terms of fitness for purpose for the users. Steps have been done within Aspect to address this, but we also have still the example that was proposed by Nick, for example, or even Ichi about the downscaling. How can we make this large-scale signal relevant where there is predictability also at the local scale? This is still an open question that we cannot fully answer, and this would be certainly make the data better for several user-oriented applications. This also because to a certain extent, these data are not fully embedded into the user workflows in an operational manner. And actually, for example, we have some examples where Aspect really help to do the steps into this direction, but still a lot to do in terms of upscaling. So reaching more users, reaching organizations vertically, exploring more functionalities, and actually deciding when a specific pilot or example is mature, enough. We know that maybe this has been designed with specific co-users, but these co-users are not representative of a large, broad target user population. This is, for example, another limitation. And then, the classical one, skills and training gaps, they probably are addressed with these different elements, and also, lowering the barriers by developing successful and very easy to use kind of user-friendly applications. This also would help. And I would not forget about these emerging AI-related challenges that are not part of Aspect, but I think we need to take this into consideration. This offers strong potential, but raises a lot of issues about transparency, reproducibility, and trust. We need to take this into consideration to lower these barriers.
Thank you very much, Chiara. I don't know if Albert want to add something on this.
Yeah, thank you. So yeah, beyond also the challenges about the seamless predictions, also in general climate predictions has some challenges, okay? Because we are talking about probabilistic information, where some users are used to work with deterministic information, the tailoring information that Chiara was mentioning. Also, some users they already have a specific workflow, work in a specific manner with a specific data. So to do some changes in their way of working, it's not easy. So to address this, something that two main aspects that we have been doing in the project is to select some specific champion users. Okay, so specific sectors, and within these sectors, so relevant users that in the end they can represent the needs of the sector, to really work with them and to engage with them and to work together to develop the science, and also to develop the science and to evaluate the results from their perspective. Okay, so with our statistics, we can evaluate the temperature, if we're improving the temperature, whatever, with some statistics, but also to evaluate from their perspective. Okay, so taking into account their decision making process, and also to quantify economically the added value of having this information or not. So, and I think that this can be a good example also for the upscaling that we were mentioning before.
Thank you very much, Albert. Now, we talk about barriers and challenges, but now I will change a question about facilitating uptake. So, Chiara, for example, what can a climate services provider like the European Center for Medium Range Weather Forecasts do to facilitate wider adoption in the future?
Yes. So one important element is really bridging and filling the gap of research to operations. And we are learning a lot from the operationalization success of the weather forecasts, and especially also thinking of these new AI-based systems. And this, of course, imply many different elements, including very technical things like documentation, quality control, traceability of the products, user support, being responsive and reliable, being agile, and always present which are also the limitations, disclose the limitations and assumptions to the possible extent. We need to focus on this reliability. We need to focus on robustness and usability. We need to make an effort on leading these standardization frameworks and governance frameworks together, of course, with the partners, because this is best practices that are found via a consensus process. We can work more on lowering the access barriers via, for example, unified platforms. I think this is a bit what the C3S and the Climate Data Store is doing, but like supporting this kind of CDS-like catalogs, APIs, supporting more user-oriented applications, making data more actionable, training, practical guidance, but also sharing examples, again, as a way to upskill.
Okay. Thank you very much, Chiara. Now, like before the final question about the future and so like the trajectory, now we like a question. It's written that like, are we going to have end user data product from aspects such as like bias corrected, high resolution information, and its usage toolkit based on what we learned on consistency, seamlessness across the timescales?
Maybe I can start to answer this question, and maybe my colleagues would like to complement. From the side of making this information available to the possible extent, in terms of give you access to the data, exactly the data that were used in these case studies. I give you access to the methods. I give you as detailed as possible on how we develop different elements. The answer is yes, there is a way of sharing this information outside. And I think Harry has also quickly presented some of the interfaces we are working with to make this kind of a consistent. But of course, within Aspect, there is not an operational access to this information. That's an important message.
Thank you. Thank you very much, Chiara. Now we have like time for our last question about the future and the trajectory of the project. So, what are like the current research gaps in seamless prediction, and what further research is needed in this context? So, now I'm asking like to Jason. So, what do you expect the future impact of this prediction to be for society in different sectors?
Yeah, so firstly, Aspect isn't over yet. We've got a little time to run, so there's some of this we can do in Aspect. And I think one of the really exciting parts of the research that we've still got in place is adding more understanding to why we see particular outcomes in the predictions, and in particular, whether the physical mechanisms are represented in the same way in the models that are focused on particular timescales. And I think that's really important to something Chiara said, that it's important to demonstrate the credibility of the systems that we're talking about here. If we think about where we're heading into the future, I mean, from a scientific perspective, it's clear that we haven't reached the limits of skill. We can tease out more skill. And I think being able to extract that skill on that timescale, all the way from beyond a 1 month timescale out to probably the 20, maybe even slightly longer horizon, still needs to be top of the list. And the reason for that is we've heard about barriers, but one of the biggest barriers is that many user decisions, they are simply not set up to use relatively small amounts of marginal skill gain. And those case studies where I think we've seen most success, and we have seen that within this project, are those where there's been a lot of consideration of how to use those increases in skill. So I think we will see more work to push the skill forward. That might involve more work with multiple systems. It might also involve recognizing that systems may not all have the same weight. Some systems are better in some parts of the world than others. So how we combine results into a multi-model system is really important. We'll see continued focus on understanding the signal to noise issue. We've got partway in this study, there's been some really nice advances. I'm thinking some of the work of Doug Smith, for instance, around the impact of how water vapor is represented is really important. I think there is probably a lot more to do on going to finer spatial scales and looking at the local drivers of skill. There's certainly still more to do on extremes and saying, look, what information can we get on the extremes beyond the weather forecasting time scale? Again, I think Aspect has laid some of the groundwork for doing this, but now we need to take a twin track approach. We need to pull those items that are mature enough into operational use, and those items that are still in the research domain, we have to really target those parts of the research question that most closely relate to user need. I think on the social science research side, there is work to do in understanding which decisions are most sensitive to this type of information on different timescales. There is probably work to do about how we embed these tools in smaller enterprises rather than medium-sized and larger enterprises where there are large terms. I think there is further work to do around understanding how to really embed scaling. And we've heard from some of the mechanisms that are really working with scaling, including more accessible data systems, training, etc., and standards. I think having more examples of how they work in different user contexts is really, really quite vital. And then the final one I'm going to pick is we've heard of the potential roles of artificial intelligence. I think when we look at a project like Aspect, we can actually see many different ways we might use it. I think we will see it within the physically based models, replacing some of the schemes. I think we will see some foundational data-driven models that will be really interesting to see, building on the sort of demonstration we've seen from the literature from people like Chris Kent. I think we will also see AI helping us with some of the quality control and quality assessment questions. And one that really excites me is that I think we will see AI-based climate consultants eventually emerging. We're already seeing some of those agents starting to be demonstrated. But I can imagine those agents actually helping people choose the right climate product for the question they have, and making it more effective to really start to address resilience or operational optimization questions without fear of picking the wrong data.
If
Thank you very much.
Sorry, if I may add a quick comment on this last point of Jason. Thanks, that is very relevant. Just let's remember that this AI quality tool, that this is a bit where also we are going in a climate service perspective, should be by themselves quality controlled. So
absolutely.
Yeah.
I think, I mean, since you've raised that, I can't resist coming back as well. I mean, it raises that question of trust across climate services. And I think that is difficult enough to demonstrate when there's a human in the loop. Figuring out how we actually benefit from AI, and there may be benefits because of that scaling. But the trust aspect, I absolutely agree. There's loads of research to do there.
Cool.
Well,
Thank you.
just to complement what Jason said, I think that we started with Aspect, and I think that we need to learn more about the way that we implement the seamless and how we tailor it to the specific application. So, for instance, at BSE, we're working with two super users, one company in Catalonia and another with Save the Children in Western Africa. In both cases, a similar question appears, so drought events, but the way that we approach it's different. And for instance, in Africa, so the skill of El Niño, it's helping us a lot to improve the predictions and to select the specific members. But in Europe, so it's different. So having these different situations, working with different variables with different timescales. I think that there is a lot of place to learn and then also to put it operational, because we need to also to see how it works in a real operational manner.
Okay, so thank you very much. We came like an end of the session. I would like to thank like all the panelists that have been involved yesterday and today as well for their intervention, and thank you very much to you for all that you have like participated. So regarding future updates, we will record these 2 days of intervention on our website, and then like would like to also update the participants that we will share all the news and all the upcoming activities, for example like the training session that we have like through our channels. So please like stay tuned and follow us for the next steps and next actions. So I also want to say like thank you all the speaker, all the aspect scientists, and also like who work behind to organize these 2 days. Thank you very much. Thank you very much.